Live.
Okay. My two dogs are cuddled up with their butts facing towards me.
So you're like receiving their gas attacks.
Yes.
Yeah,
Yes.
no, that Carla's out for lunch with a friend, and the dog is completely used to always having 100% access to Carla all the time. And so the fact
Oh
that
no.
she's not here is a great distress. And so the dog is in the room with Chloe, and all she wants to do is get out and look around the whole house for Carla again. And she'll just do that. She'll nonstop. Like if we didn't put her in the room, then she would just go up and around the house. You would hear tick 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 tick. And she
Yeah,
in.
apparently Malachi does that when I travel. And he's in for trouble because I travel a lot.
Yeah.
But yeah.
Okay. Yeah, I don't even know what we're gonna do when we both travel. We're gonna be for us. I think we're gonna do this trip in December, and so we're gonna
Hmm.
someone's gonna babysit the dog for 2 days.
Well, Chloe's old enough to be home
Oh yeah,
alone.
Chloe's great, and she's offered, so I'm sure she'll be the one. And the dog loves Chloe, but dog
Dog
really
has
loves
good
Carla.
taste.
Yeah, yeah, dog really loves Carla.
I get that.
Um, Fraser should attach a dusting mop to the dog's tail and let it clean up the place. It's a good call. I like that. Okay. I never said hello. Man, I feel bad. I'm gonna say hi to people. Hello to Adam Synergy, Arts of Space, Beth Johnson, Borit Klenkar, Dustin King, Esther Gagne, George Lancaster, Gordon Dewis, Guido Bieber, Johnny Zed, Kylie Cerna, Larry Beckham, Mr. Tom Harbin, Paranor, Paul Gracie, R. Instro, Rich Wilson, Rich 901, Sergusi, and Susie. Hey, everybody. Welcome back to this second episode. Now, people are getting weird notifications from YouTube about things happening and new things happening. I think it's because Susie scheduled the two shows, one at 12 and one at 12:30, and then the 12:30 went over. And I guess YouTube just tells you that it's happening without it actually being a live stream. But then
Oh.
they do get the same. I think they get the same streaming code. So, huh? I don't know. Like technology, come on. There's no rhyme or reason to it. There's no working with it. Anyway, so we
There
will.
is working with it. There's just not sensible working with
No,
it.
no, there's just being frustrated with it. All right, let's. Esther has a question. Whoops. Oh, okay. All right. Our Esther's answering it. Okay, let's begin. Are you ready?
Yep. I am pressing record. It is recording.
I have also pressed record. Here we go. Astronomy Cast, episode 551, Missing Epochs, Observing Before the Cosmic Microwave Background Radiation. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I am doing well. How are you doing?
Doing great. For people who maybe didn't catch it, I had an absolutely fascinating interview on my channel with the director of, and I forgot his name, so I'm gonna have to say this again. Susie, now it's my turn to mess it up. Um, Jason, I gotta get the pronunciation right. You know what? We'll skip that part right now because I don't have it in front of me. I'm totally logged into this YouTube channel, so if I go and check my other YouTube channel, that's gonna wreck it. So anyway,
Right.
so you just cut all that out. It's easy. Um, how am I doing? I'm doing great. We are recording at funny times. Time and space have no meaning. You are somewhere, probably in an airplane or visiting friends somewhere. I might also be in an airplane attending a Christmas party in California, maybe. So everything's just going to be up in the air. But we are recording ahead of time so that the schedule, when these shows come out, happens right on time. That's the plan. We're so
It's a good
organized.
plan.
Yeah, I've really got to give all credit to Susie. I think for making sure someone is thinking far ahead and saying, these are the weeks that episodes have to come out. What will it take for Fraser and Pamela to record in advance? Our old plan was to just, not or catch up. Susie is ahead of the game. That's
Susie is what keeps us
yeah.
going. And all of you who pay into our Patreon program, you are awesome. And you let us pay Susie, which really means you let her kids go to college.
Yeah.
So
Yeah,
double yay.
you're sending Susie's kids to college. Thank you from them and us.
Mostly us.
The cosmic microwave background radiation is the earliest moment in the universe that we can see with our telescopes, just a few 100,000 years after the Big Bang itself. What'll it take for us to be able to fill in the missing gap, to see closer to the beginning of time itself? All right, first, before we get into what it's going to take, what is it?
All right. So last week we talked about how there was the point in time when the cosmic microwave background was formed. Well, we're now turning the clock back even further. So when our universe became a thing, it went through all these crazy steps of forces dividing and stuff like that, leading into the epoch of inflation when there was runaway growth as some sort of a scalar field propagated through the universe, leading to everything bloating up very rapidly and in a way that causes everything to look basically the same in all directions. Then, after this, we were left with a still way too hot, still way too dense universe in which initially you couldn't even have protons and electrons. Then it cooled enough that you could get those, at which point there was runaway nuclear reactions. We got hydrogen and helium, bits of lithium and beryllium. Then it cooled off enough that all of those nuclear reactions stopped, but you still have this big, dense soup of a universe that has sound waves left over from those nuclear processes propagating through this early universe. And as they do, they're building up areas of higher and lower density, creating what we now see as the power spectrum in the universe. That's way oversimplified. Any of you who have a PhD in cosmology are now cringing.
Yeah.
We're doing the big brushstrokes here,
Right.
folks. We're doing the big brushstrokes here.
Okay, so when you say the power spectrum, what does that mean?
So, when we look at the cosmic microwave background, we see a distribution of places that are a little bit colder and places that are a little bit hotter, and they come in a variety of sizes. And when we look at the distribution of their sizes, we see this set of peaks and troughs that we refer to as the power spectrum of the cosmic microwave background. Um, those sizes are reflective of the characteristics of the early universe. If we saw a different distribution than what we see, it would mean that all of our ideas of how all of this happened are wrong. And luckily, when we got our first good measurements using WMAP, what we saw matched what we thought we would see, which is always a good thing. And as we've continued to revise, we have more or less continued to see what we expected. There's been a few missteps along the way, and unfortunately, those missteps occasionally get more attention than they should and are related to the gravitational waves that are the primary topic of today's show.
And when we imagine the cosmic microwave background, I mean, the pictures that we see of the cosmic microwave background are this sphere, or sometimes it's sort of a flattened sphere, that it has different colors on it, kind of greens and blues and reds and yellows. And when we're looking at that picture, what are the greens and reds and yellows and blues that we're all familiar with?
Those are tiny, tiny variations in the precise color of light that was released during the creation of the cosmic microwave background. And those slight point to point variations in color are characteristic to differences in temperature, which map to differences in density
Right.
at different points in the early universe.
And so when we see that ball of universe, we're seeing really just places that were less dense and places that were more dense before the cosmic microwave background. And this is sort of going to start to help us sort of figure out how we can maybe even begin to probe into this area. And just, I mean, I think when we see that, we imagine, when we look at that picture, we kind of imagine this ball that is growing. And that's unhelpful, because that's not
Right.
what it is, right?
No.
I mean,
So a better way to think of it is if you've ever gone walking in the fog with a flashlight, if you hold the flashlight straight up, it will illuminate a column of light, not a sphere, a column. Where it's not a perfect analogy. That column that surrounds you, which is as far as the light can go before it reflects back off of the fog, that is your visible sphere. And as you move through the fog, you take your visible sphere with you.
right.
Well, in the case of the cosmic microwave background, as we move through the universe, if we were able to suddenly teleport 5 billion light years to the left, whatever the heck light year, whatever left means in
Yeah.
the concept of our
Yeah.
universe,
The opposite of right,
um,
obviously.
clearly,
Yeah.
were we to make this sudden jump, if we observed the universe around us, we would see a different specific pattern of cooler and hotter, longer and shorter wavelengths of light. But the pattern of how many there are of this size, how many there are of this size, how many there are of this temperature, how many of this temperature, that pattern should be reproducible no matter where we're observing it from. So we just happen to be seeing the light that was given off by what is now at the appropriate distance.
Right.
That wall is seeing the light that was given off from where we are right now. This light is traveling in all directions. You're going to see it no matter where you go. You're just seeing a different cutout of the universe.
And that idea that you, like, when you look off in all directions and you see the cosmic microwave background in all directions, you are just seeing this moment 300,000 years, 350,000 years after the Big Bang, and and from everywhere in all directions. And it just happens to be that it's coming from a certain distance away from you. And then every year that goes by, that sphere around you that you're able to see this is one, is bigger, and you're now seeing more of the stuff that you had seen last year. Now you're seeing the universe that is a little bit older now, and so you don't see the cosmic microwave background from that spot because now it's gone past you. But now you're seeing the stuff that's a little bit older and a little bit farther. It's such a head scratcher, of an idea, but it's like, until you can get away from that idea of you're just imagining this sphere that's expanding, and
Yeah.
that's what you're seeing, your instincts can always be, taking you down the wrong path because it is not how you're imagining it.
No, and one of the best possible ways to imagine is you are in a ginormous sponge. You carve a sphere out of the sponge and stick yourself in the center, and you're seeing one wall. You pick yourself up, move yourself to a different part of the universe that isn't within the visible universe you have now, carve out a new sphere, and you're going to see a new part of the
Right.
sponge. But the sponge overall should, if it's well made, be basically the same everywhere. Sure, the specifics of where the gaps in the density is, those specifics will vary,
Okay.
but the distribution of voids and structure should be reproducible.
And so then, and the reason we can't see beyond the reason we can't see behind the cosmic microwave background is because that before that moment everything was opaque, and so there is this
Right.
missing 330,000-ish years from the Big Bang to the release of this radiation. We can't
Yeah.
see it. So how can we see
380,000,
it?
400,000.
Yeah.
Don't
How
add us.
how will we find that? How will we learn anything about what happened during that time?
Well, we've been trying to get everything we possibly can out of the cosmic microwave background light. And one of the hopes was that we would see in its polarization the signature of gravitational waves that would have been ricocheting through the early universe that should still be rumbling across the modern universe. Now, unfortunately, the background imaging of Cosmic Extragalactic Polarization Instrument, or BICEP, they published all of their results a number of years ago, and they were like, we found the polarization. And then everyone looked at the results and said, cool, dude, you forgot about dust. They forgot about dust.
Yeah.
Well, they didn't forget about it. They just didn't realize that what they were actually seeing was polarization due to dust instead of due to gravitational waves. And so we continue hoping that we'll get better measurements that are able to overcome the dust, able to instead see polarization due to gravitational waves. But seeing the effect of a gravitational wave isn't as cool as seeing the gravitational waves itself. And I went on a deep dive down the rabbit hole of papers on what are called primordial gravitational waves in preparation for this episode. And first of all, I'm going to say I found some of the worst written paragraphs and most wordy sentences I have ever come across. But in addition to having some just really unnecessarily complicated verbiage, I, what I also saw was the hopes and dreams of a lot of theorists who believe that while we'll never be able to detect these kinds of gravitational waves here on the planet Earth, now that we've proven that we can find things on the planet Earth, there is a chance that we'll be able to someday build new and better and able to resolve different frequency of gravitational wave detectors that are built in space instead.
Right. The follow on to, I mean, Lisa might be able to just barely be able to see it, but the follow on version called the Big Bang Observatory, Big Bang Observer, it's going to be a mega Lisa.
Yes.
And so
And
that might do the trick.
and Lisa itself is and the plans on this update regularly. So I'm going to be vague for those of you who are listening in the future. Uh,
This is a
Lisa
future
is
telescope.
It's a future telescope, but it's a future telescope that has been aggressively advertising itself for about 10 years now. Longer than that, I think.
And one component has already been tested in space, the Lisa Pathfinder. So it's, it's like half a telescope.
It's making progress, sort of, for small values of progress. Uh, so Lisa is set to be a constellation of satellites that are interconnected through lasers and are shining light between each other and potentially a central detector. And due to very careful understanding of their orbital paths, they will be able to differentiate between motions that are due to being in space and orbiting, and motions between the different spacecraft that are instead due to the ripples in the space-time continuum that occur when a gravitational wave passes through. We actually, as uncomfortable it is to think about, get stretched and contracted when we are under the influence of a gravitational wave, not at a level that you will ever notice. And since your pants are getting stretched with you, unlike on Thanksgiving, it's not an unpleasant experience, but it's the kind of thing that we can detect by the changes in how light interferes. When you shine a light, a laser in particular, where you have collimation, depending on how different reflections of that laser interact, they will either create a bright spot or a dark spot. And there's actually a fringe of all of these different bright and dark places in the interference. And as the spacing changes between the different reflections, that pattern of interference changes. And that's what we're looking for, is the change in the interference pattern.
And you can kind of imagine Lisa as like three buoys floating on the ocean with waves passing over them. And a wave passes over one, and then the wave passes over another one, and the distance between the buoys will change as the waves pass over them. And it's the same thing that's happening with the interferometers that are happening here, like LIGO here on Earth, but just out in space. And the arms will be a lot longer. They'll be like on the order of 10,000 kilometers, right? They're going to be very carefully tuned. And then, and in theory, Lisa will be able to see the loudest gravitational waves given off by earlier moments in the universe beyond the cosmic microwave background.
And the catch is, what is the frequency of the gravitational waves? And this is a really hard thing to imagine. Different objects send a wave of a different size through the universe depending on how they merge or just how they come into existence. So our galaxy is on a regular basis just sort of rumbling out a steady background of really, really low amplitude. We're never going to detect them gravitational waves. Well, during the earliest parts of our universe, those first few hundred years, that epoch of expansion, the inflation part, that would have a gravitational wave signal. The sound waves reverberating through the early universe would have had a gravitational wave signal. Now, the question becomes, how much of this is simply a noise where we can't make sense of all of these different waves? And what of this can be detected? And then there's other really cool, intriguing things to think about. Like, we talk periodically about primordial black holes, and if Hawking was correct, and black holes are decaying through Hawking's radiation, none of these things still exist. But we might be able to detect the mergers of early primordial black holes through gravitational waves.
Right.
We just need to have instruments we don't currently have.
So, I mean, that was sort of two separate things, right? Like, one is like maybe there were these black holes that were formed during the Big Bang, shortly after the Big Bang, with overdensities in the early universe. Those might have formed those first primordial black holes, and then the ones that we see later on, the ones that formed from star collapse or infalling gas, those come later. And so we could detect those smashing together before the universe was even visible with some of these future instruments, which is a mind-bending idea. There was one idea for a large-scale gravitational wave telescope that I really liked, where one arm, like imagine a big triangle, big equilateral triangle. One arm of the triangle is at the L4 point, one of the Earth Sun L4 point, one is at the L5 point, and one is at the L3 point. So on the far side of the sun, which is generally a useless place to put a spacecraft, but you then get an equilateral triangle. And even though sort of things are moving around and there's orbits and the Earth's path isn't entirely circular around that, by moving the spacecraft in sort of lockstep with each other, they should be able to keep them within like a few hundred kilometers at the worst point of keeping the legs of this gigantic interferometer together. And so you make a telescope interferometer the size of the Earth's orbit, a LIGO, a Lisa, where the legs are, more than 100 million kilometers, which would be great.
And
that could do it.
And this is pretty much the only way we're going to get any information out about the age of inflation. We need to look at gravitational waves. And gravitational waves also may be the only way for us to finally put the nail in the coffin of some of the more exotic particle theories. Some forms of string theory, for instance, have gravitational waves from primordial sources occurring in the early ages of the universe. And by looking at what we do see and what we don't see, that will put restrictions on what the early universe was. And currently, we don't have anything other than that CMB. And that's all we've got.
Yeah. Now but the CMB itself, those different temperatures that we see do correspond to overdensities and underdensities in whatever it was before that. So,
yes.
I mean, there are methods that you can use just the cosmic microwave background to probe what must have come before. And then you match that with the math that we have to get a sense of what was going on in there, right?
And this is where you have to remember that there's often more than one way to get the same outcome. And theorists will always find wiggle room to come up with a new theory if you don't give them enough constraints. So yes, we can do a whole lot looking at the cosmic microwave background to say, this is how things should have happened. But inflation is still very much a large black box labeled here be inflation with whole lots of different theories to explain it. And it would be nice to have just that one extra point that you have to match. Gravitational waves can provide hopefully more than just that one extra point. We're talking about 400,000 years where we went from nothing to everything. And currently we only see the echo of that time. Let's get in and see that time directly.
So apart from gravitational waves, are there any other techniques at our disposal that would allow us to see before the cosmic microwave background? It's only going to be gravity.
It's only going to be gravity because other than gravity, we don't have any forces that carry long distances. So of the four major forces, only gravity and the electromagnetic force carry for great distances. Only light, which is a particle, travels for great distances.
Right.
We don't have cosmic rays coming from primordial times. We have the light that was released with the cosmic microwave background. That's it. That's all we've got.
So, but I mean, you're saying a thing there, which is making me think. You say we don't have cosmic rays. So, but I mean, would there be any particles that could be released? Because I mean, particles were being created. Protons and heavier elements were being created in that time before the cosmic microwave background, before the light could get out there. So could there be particles that were being emitted or not emitted, but are still around from that time? Or is that just what, I mean, we know that the universe, by measuring the amount of hydrogen and the amount of helium and the amount of lithium, et cetera, and beryllium, that tells us what happened during that period. And it perfectly matches the predictions of the Big Bang. So
there are string theory models. And we all know how I feel about string theory.
Right.
There are string theory models that say that there could be superstrings or other exotic particles left behind that may be detectable. So far, they haven't been.
Cosmic strings.
Yeah.
Yeah.
So I don't think so.
Right. So there might be, some theories say that there might be structures that are out there in the universe that could explain this. Someone's at my door. I got to go grab this. Hold on. And then we'll wrap it up. Why
Okay,
don't you say the
sorry,
names while
everyone.
I do this?
Okay, Susie, you're gonna have to rearrange audio. We are sorry. We are very sorry, Susie. All right. Okay. As we do at the end of every episode, I would like to take this moment to thank all of you that make everything we do possible. We couldn't be here without you and your generous contributions that let us pay Susie, who is our audio producer, our chief cat herder, the person that keeps Fraser and I organized and on track week after week. And these are the people who've been contributing at the acknowledged on YouTube and acknowledged in the show level on Patreon. I would like to thank A Blip in the Universe, Carton Spar, Ed, Stephen Shewater, Gordon Dewey, Bill Hamilton, Frank Tippin, George Thorwald, Richard Riviera, Alexis, Thomas Sepstrup, Frederick Hogney Kvam Jensen, Sylvan Westby, Jeff Collins, John Drake, Arctic Fox, Merrick Verdarney, John Vance, Nate Detweiler, James Platt, Ron Thorsten, Philip Walker, Elad Avron, and Cooper.
Thank you, everybody. And thank you, Pamela. And we'll see you next week.
Sounds great.
All right. Stop that. Save that.
Okay.
That's 5:51.
There we go.
Okay. So, I think my Christmas present just arrived.
Okay.
Yeah.
Stop. My
So
dog just arrived.
I won't open it up.
Hi. Hi.
Okay. That's
have a puppy.
all saved. Did you want to take like 10 minutes and answer some questions? You got to run.
I'm good for about 10 minutes. I'm
Yeah.
expecting a phone call at some point.
Okay.
So this is me plugging in my phone.
So this came early on in the conversation. This came from Hal McKinney, which is, how could the universe not have background radiation regardless of whether there was a Big Bang or not? So I guess the discovery of the cosmic microwave background was like this was considered this smoking gun to say, haha, the Big Bang theory is right because it predicted that you should see this radiation, and you did.
Mm-hmm.
So if there wasn't a Big Bang, say if the universe had been always around forever, would you still see some kind of background radiation?
Well, it wouldn't so much be a background radiation like what we see. It would be a combined light from stars at increasing distances. Now, this is similar to when we look out and we start adding up the light from all the distant galaxies, and you end up with the universe as the color of a latte. In this case, it's just cumulative starlight would form a background.
Right, and so we actually do see that. You talk about this cosmic latte, that if you take essentially the color of the light from everywhere across the whole universe and you average it all out, you get this kind of latte color. So, Astro B asked, what is faster, cosmic expansion or light speed?
Cosmic expansion.
Is it though? I mean,
well, in the epoch of inflation, the
okay,
I believe was
faster than the speed of light. Yeah, but doesn't it? I mean, aren't you always sort of having to ask by what distance?
Right, and so that's the thing.
Right, and so if you look at a place that is, say, 46 billion light years to the left of us, and again, whatever left means, and 46 billion light years to the right of us, then those two spots are moving away from each other potentially faster than the speed of light at some point.
Right.
in the past or future. And so, but if you have two places that are right next to each other, then they're not moving away faster than the speed of light.
Yeah.
And like say the Hubble constant is not moving. It's 100, what 77 or 76
How we don't know.
kiloparsecs per second.
Somewhere between 65 and 75.
Right. And that is not faster than the speed of light. Or is it? Yeah. Hold on.
Well, but the
Depends on the
catch is
distance.
it's per megaparsec.
Per megaparsec, yeah. And so if you're going to
Yeah.
measure from, the entire side of a megaparsec, then those two parts are definitely moving away from each other faster than, yeah. So it really just, it all depends on distance. Let's see. Any other questions? It's fine. We don't have a lot of questions. Let's see if there's any from the previous one. So Paul Gracie during the last one was talking about how gravitational lensing is using a galaxy-wide telescope, is it not?
Yes.
Yeah.
I wouldn't call it a telescope. That implies two optical elements. Definitely a magnifying glass.
Yes. And the joke that I always like to make is that we don't know what dark matter is, but we know how to use it as a telescope. Very precisely, we know how to use dark matter as a telescope.
Yes.
Which is awesome. You could have some place that is invisible or not invisible. Yeah, invisible. And yet it has an overdensity of dark matter. Therefore, it provides a gigantic gravitational lens. Therefore, you can use that to act as an additional lens in front of the rest of your telescope to observe objects which are farther away. So thanks, dark matter. We don't know what you are, but thank you.
And I apologize for the dog. Eddie knows how to open my office door by bumping the handle just right. And so all three dogs are in here, and this one will claw my arm until I either pick her up or take her OUT.
Right.
So.
But you can't spell.
This allowed us to get through questions.
Wow, there's quite an argument going on in the chat. And unfortunately, now I can't see any other questions. Okay, Dustin King asks, since the universe has expanded, could we see things that were previously smaller than the Planck scale?
No. No, because things that were smaller than the Planck scale, that's not.
It's okay,
a thing.
you can let her out. Yeah.
Are you still going?
Yeah, but we're just about to wrap up. So, but I mean, if you had a thing back at the beginning of the universe, right back before inflation, say, and you had some region that was the size of a Planck, which is some very, very, very small number, and then you had the inflation process after that with
an empty piece of space smaller than the Planck scale will be bigger, yes.
Yeah.
But a thing
right. No, it would have been an empty piece of space filled with the inflaton field, and now it'll be whatever has resulted from that. That will be big, right?
Yeah.
Which is mind-bending.
You can always expand an emptiness.
Right, yeah.
Emptiness is good that way.
Yeah, absolutely. Mokopa, do you have any thoughts about X17? You've been looking at this potentially fifth force?
I decided to ignore it until there's more papers.
Yeah. The gist is, I mean, the people that we covered it on Universe Today. Brian Koberlein wrote the article on that, and Ethan Siegel over at Starts With a Bang did his version. And the gist is, this is interesting. It's probably not a fifth fundamental force, but there might be a fifth fundamental force, and that's interesting.
Yeah.
So we're not there yet.
Yeah, the thing that got me was the New Science article looking at the biological results of Scott and Mark Kelly's experiment.
Oh, yeah?
Where basically human beings really don't do well in space.
Yeah. One thing that's actually really interesting is that Cancer apparently has trouble in space. Heard about this?
Unfortunately, the immune system doesn't recover fully, is what they're finding.
Right.
And it's the part. So once you get back down to Earth, you could be at a greater risk.
Yeah. But like, cancer apparently maybe requires gravity to know how to expand. And so they did some microgravity experiments with cancer cells and found that it confused it. And so, in fact, you remember in Contact, where the rich, billionaire was in orbit because he was old and sick. Maybe he's right, and he will, that in fact future cancer research will come from, or future cancer treatment will include a free trip to space.
Yeah, more research is needed.
Absolutely, and that's what the researchers said. But it was a really interesting thing that was going on. So, let's see. I think that's it. Let's wrap things up.
Okay.
For
I know my
this.
dog wants OUT.
Yeah,
so.
yeah. I've got a dog here that's getting a little squirrely as well. So, hey, thanks everyone for watching today. Thanks for everybody who was chatting in the chat and moderating in the chat. All the folks on Twitch, you're not forgotten. You've been able to watch this whole episode. Good job on you. We will be back. I guess we won't be recording this Friday. We did that today. We won't be recording next Friday. We did that also today. So it'll be 3 Fridays from now.
Which will be prep, I believe, for the Hangout-a-thon.
Okay. And then shortly after that, we'll be hanging out in person when we're going to be in Honolulu at the American Astronomical Society. So we will try to do some kind of live stream. It all depends on how good of an internet we can get from the middle of the South Pacific.
Well, and at least we won't have dogs.
That's right. Well, I'm sure we will find some Hawaiian dogs to hang out with us while we do our recordings. It won't feel right without us having to split our attention between dogs. Hold on a second here. Hold on. Here, over here. There we go.
That is just such an adorable dog.
Yeah. She's a good dog. Is this too weird? Can you see the dog? Well, we're watching His Dark Materials, and they've got a polar bear. The polar bear in the show. Yeah. That is really interesting. Let me see if I can make. See if she'll see your dog. Oh, she does. Okay. Do you see the dog up there? Can you make her like move around? Can we get them to see each other? What's this gonna take?
Stella, what's over here? Look over here. No, don't look at me. All right, let me move you to a different screen.
Oh, you see it over there? To the big screen that has the dog on it.
Okay, Stella, look over here. Look over here. See? Over here. Stella's having nothing to do with it.
No, she just wants to cuddle up. All right.
Yes.
Yeah, I think Ona sees it. All right. Thanks, everybody. We'll see you all in a few weeks.
Okay.
Bye. So.
Yeah. Stella is